Your query runs fast sometimes, slow others. The difference is often measured in milliseconds of disk input-output. When analyzing query performance, the raw execution time is misleading without context. We need to quantify the actual input-output cost. The buffers section in PostgreSQL's Explain Analyze provides this quantification. It details exactly how many blocks were retrieved from shared memory versus how many required physical disk reads. A single block read from disk can cost thousands of CPU cycles compared to a cache hit. This section is the definitive metric for identifying input-output bound queries before you even look at the plan notes. The buffer's output is structured around shared and local memory. Shared buffers are the primary cache for persistent tables. Local buffers handle temporary objects created during the query execution, like hash tables for joins. If the buffer section is missing, you forgot the analyze keyword. Always include buffers explicitly for deep performance analysis. We start with shared hit, which counts blocks found directly in the shared buffer pool, indicating zero physical input-output cost for those blocks. A high count for shared hit is ideal. It confirms effective caching. Conversely, shared read counts blocks that required fetching from the operating system cache, or worse, directly from the physical disk. A high shared read count immediately flags a potential bottleneck. This indicates either the shared buffer size is insufficient or the working set of data for this query exceeds the available cache. If shared read dominates, investigate the effective cache size parameter and the query's access pattern. Sequential scans often lead to high reads if the table is large and uncached, demanding immediate indexing or partitioning review. When data modification occurs, we track shared dirtied and shared written. Shared dirtied counts blocks modified in memory but not yet flushed to disk. This metric indicates pending write load that the system must eventually handle. Shared written counts blocks that were actually flushed to permanent storage during the query execution, typically by a checkpoint or background writer process triggered by the query. High shared written suggests heavy transactional load or inefficient batching. This metric is crucial for understanding transaction commit latency and overall system input-output pressure. Local buffers are often overlooked but critical when dealing with complex operations. Local hit and local read track temporary table usage, such as large sorts or hash aggregates that spill to disk. If local read is high, the query is generating temporary files that exceed the work memory parameter. This forces the database to use disk space for intermediate results, drastically increasing execution time. The immediate action is increasing the session's work memory parameter to keep these temporary structures entirely in memory, eliminating costly disk spills. Moving beyond input-output, the timing metrics provide the temporal breakdown. The first split is between planning time and execution time. Planning time is the duration required by the optimizer to generate the optimal query plan. High planning time, especially for simple queries, often points to outdated statistics or complex view definitions requiring extensive rewriting. If planning time exceeds 10% of total execution time, run analyze on the relevant tables immediately to refresh the statistics used by the planner. Execution time is the actual duration spent processing data. Within the plan nodes, the key metrics are actual time and rows. Actual time is presented as a range, the time elapsed before the first row was returned, and the total time until the last row was processed. The difference between these two values reveals latency in the initial data retrieval versus the overall throughput. High initial time suggests slow startup costs, perhaps due to index lookups or complex initialization steps that delay the first result. The loops count combined with timing is essential for identifying skew in parallel plans or inefficient nested loop joins. If a parallel worker node shows significantly higher actual time than its peers, data skew is present, meaning one worker processed a disproportionate amount of data. For nested loops, if the inner loop execution time is high relative to the number of loops, the index access is inefficient or the index is not covering the required columns effectively, leading to excessive input-output per iteration. The true power of Explain Analyze is correlating these sections. If a specific node, say a sequential scan, shows high execution time and the overall report shows high shared read counts, you have a direct input-output bottleneck tied to that scan operation. If a hash aggregate node shows high time but low shared read, check the local read buffers. This indicates a memory constraint, specifically work memory, rather than a persistent storage input-output issue. Use the buffer metrics to diagnose the root cause of the high execution time. Based on the analysis, tuning is precise and evidence-based. If shared read is high, increase shared buffers, or optimize the query to use indexes, reducing the volume of data scanned. If local read is high, increase work memory. If planning time is high, update statistics. Never guess, the buffers and timing sections provide the empirical evidence needed to justify specific configuration changes or query rewrites, ensuring performance improvements are measurable and targeted to the actual bottleneck identified.